Hello and welcome to the RLabs tutorial on exploring data. Once you've successfully brought your data into R, a first step before rushing into data analysis is to explore the data and try and understand its properties and composition. A first approach may be to look at the raw data. This can be done through using functions like head, tail, and view. After that, you may want to consider what type of object the data is being stored in, as this will affect how you index it and process it going forwards. And also the properties of this data, such as the number of rows and number of columns, and even the names of these columns. This can be done separately by using functions like n row and n column, length and names, or alternatively, you can use functions like structure, str, or the function from dplyr, glimpse, which allows you to get an overview of the whole data, as well as insight into the properties of each specific column. With an idea of what the underlying data is, it's interesting to plot the data using the function plot, and possibly even inspect and associate data points on this plot with specific properties and row numbers. Finally, before moving on to statistical analysis, it may be important to count the observations that occur within the categories of your data. To do this, xtab is a really useful function. Okay, so let's get started with RStudio. In this quick intro to exploring data, we're going to first use the dataset about air quality. This is a dataset that's stored within base R, so we can just assign it to a new variable called myData. You can see that this dataset has now appeared in our data area in the top right hand panel of RStudio, and we can see some information about it. Let's go on the console though to use head to look at the first six rows of data. We can see that there's some NAs in it, and we can see the names of columns. Tail also complements this, as it allows you to look at the last few rows of data in the object. With this output from the head and tail function, you may start to consider some troubleshooting that you might have to perform in the coming steps. For instance, if a whole column was missing or was full of NAs, you may want to remove it in coming steps. Another common problem is that sometimes the data hasn't been completely written to the bottom rows of the data, and maybe some variables or all columns are just absent of data there, and these should be cleaned out to try and remove the NAs from the data early on. The class function tells us what type of class this object myData is, and in this case it's a data frame. We can then move on and ask, for this data frame, myData, what are some of its properties? For instance, the length of myData is 6. This means it has 6 columns. Another way that we could have confirmed this is using ncol, which again gives 6. A quick way to find out the names of the columns in myData is to use the names function. This is often useful when you forget the precise spellings and punctuation used for a dataset. To find out the number of rows, we can use both the length function and also the tailored nrow function. To do this, we state my.data and then use square brackets to say that we're interested in a subset, some certain group of elements within this data frame. Within these square brackets, there are 2 parameters. The first specifies rows, and the second specifies columns. Here, what we've done is left rows blank and asked it to consider the first column. In other words, this statement asks, for the data frame myData, consider all rows and the first column. Therefore, it returns the length of the number of rows. The view command is another useful way to see all the data at once. To call the view function from the command line, it's necessary to use a capital V, and this data in RStudio at least will pop up in the top left panel. Alternatively, another option is to open the data through clicking on My Data in the top right panel. If the data is larger than 1,000 rows, it will only write the first 1,000 rows to this viewing window. So don't get worried if you don't see all of the data. Calling the view function is preferable to printing out all the data in the console. When this happens, you get a vomit of data into the console and you lose track of the code that you've printed. This is not too onerous in this example with only 150 rows of data and only 6 columns, but the bigger the data, the more problematic this becomes. An alternative to printing the data and to using the function view is to summarize the data with functions like str. Here it tells us in one brief line the properties of the data, the number of observations, the number of columns. It gives us a list in rows of each of the variables. It says the type of data that each one of these columns is saved as, whether it's integer, number, or other types of data like factors. An alternative to using the str function is to use the glimpse function, which prints slightly more data to the console and gives it in a slightly neater format. One thing you may have noticed is that the month column is classified as an integer. In fact, we know that month is a categorical variable, so we may want to consider converting this integer into a factor. That is what this line does just here. We call the function factor for the column of data within my data and reassign it to its old name. If we go ahead and reprint the data and resummarize it using glimpse, we can see that the line of code above has correctly made the column month into a factor. The column month is still not perfect though. It may be difficult to interpret the categories of 5, 6, 7, 8, 9. To overcome this, we can rename these categories as May, June, July, August. And hopefully this will help with our interpretation of the data. To do this, we reassign the levels of this month variable and pass to it a list saying that we want to change the category 5 to May, the category 6 to June, etc. So here we've used the levels function to inspect what levels are included in the column month. They've now been relabeled correctly, and if we print the data again and just take a glimpse of it, we can see, yes, the first several variables are all May, and this is probably because the data is date sorted. Now we can jump in and start to plot some of our data. We can see in this bottom right hand panel that we have ozone on our x-axis and temperature on our y-axis. Possibly though, there may be some outliers that give us strange values and seem to depart from the linear relationship that we have. It would be interesting to know if we could try and identify these potential outliers somehow. Using the identify function, we pass in the same x, y variables as the plot that we've just created, and we save to a new variable, index, the points that we're about to click on. In running the identify function, it has made the plot become interactive. You'll see that the cursor has now got a crisscross mark that we can move around and click on the data. And as we click on data points, it saves the X, Y locations of these points. Importantly, once you've clicked on the points that you're interested in exploring and knowing more information about, go up here to the top of the plot and press Finish. After finishing this command, by default, the identify function prints as a label onto the plot the row numbers for the data points that we've clicked on. We can modify this to actually get different types of information printed as labels next to our data points. So let's try that. Maybe we're interested in knowing if these data points are all from one particular month. To do this, let's plot the data again, and this time add labels to equal the name of the month. You can see that before we move over to the plot, the cursor is flashing and hasn't completed its execution. This is because the console is awaiting the user, you, to go over to the plot, click on the data, and importantly, press finish. Once we press finish, this new category is printed as a label onto the graph. Finally, to give one third example of this really interesting function, let's plot the data again, and this time let's see if we can get, for each one of these data points, the precise day that this data was collected. Within the identify function, to achieve this, we're using the paste, which combines and concatenates character variables together. So we're saying we want the variable of day turned into a character as .character, and we want that to be concatenated with an underscore and the other variable month turned into a character. Let's click on the data points for one last time on the graph. Press finish, or else it won't go on and do anything. And this time we have the exact days that each one of these data points represents. This might be really useful information to troubleshooting and going forth, as you may want to look up in other data sets whether there was something special about these days, or whether our recorded value for ozone may be incorrect for these dates. Whilst this is a useful function, it has got some limitations. As you can see, if the points are densely clustered together, it can become difficult to make out what the labels are saying, because each label can obscure one another. So, the final function that I'm going to introduce you to is the xtabs. It is often the case when doing statistical analyses that you want to have an even distribution of samples for different categories. And the xtabs provides a very easy function to investigate this basic assumption. So here we've passed in a formula to xtabs. You know it's a formula because we're using the tilde or squiggly. So we're going to count how many observations there are for each month for the MyData dataset. So I hope this has presented some interesting new functions to you that will give you a helping hand as you approach exploring data. Thank you for listening to this R-Labs tutorial video. If you found this useful, you may be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.